Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Central University of Haryana, Department of Physics. Today, we are going to discuss about the module Mathematical Preliminaries-II from the paper Electromagnetic Theory. So, from this module, you will get to know about the following. In this module, we will continue to study vectors and we will come to know, taking cue from the position vector, vectors are defined in general on the basis of their properties under rotation. Then the idea is generalized to tensors of higher ranks based on the transformation properties under rotations. After that, the concept of curvilinear coordinates as an alternative to Cartesian coordinates is introduced. The spherical polar and the cylindrical coordinate systems are studied in detail. And then the concept of Dirac-delta function is introduced both in 1 and 3 dimensions, and some of its important properties are described. Rotations and tensors. In the first part of Mathematical Preliminaries Module 1, we had introduced a position vector from the point of view of its properties under rotations. We then went on to introduce certain vector differential operators, integrals, involving vectors, and gave certain well-known fundamental theorems of vector analysis, which provide a connection between volume, surface, and line integrals of certain vector quantities. In this module, we continue with the study of essential mathematical preliminaries. We begin with an extension of the concept of vectors to tensors of second and higher ranks as physical quantities having more complicated transformation properties under rotations. Rotations and tensors. Tensors. Extension of the concept of vectors to objects with more than 3 components and which have more complicated properties under rotation. So, under rotations, the coordinates behave like x prime subscript I is equal to a subscript I subscript j x subscript j, where the x prime subscript I is a coordinate which is under rotation and can be defined as another coordinate, that is x subscript j, through the coefficients given by a subscript I subscript j, where the coefficients a subscript I subscript j times coefficient a subscript I subscript k is equal to the Kronecker delta function subscript j subscript k, where the Kronecker delta function for j equal to k index gives us 1, and for all values of j not equal to k gives us 0. Vectors. Any set of 3 physical objects that transform under rotation like the coordinates. Example of the vectors are position vector, velocity vector, momentum vector, and force vector. And the transformation in the tensorial notation can be given as a prime subscript I is equal to small a subscript I subscript j times capital A subscript j, where capital A prime subscript I is the vector under the rotation transformation, while capital A subscript j is the vector under the original coordinate system, and the coefficients small a subscript I subscript j define the transformation. Now let us look at the generalization. Scalar. Physical quantities that are invariant under rotations, for example, mass, temperature, energy, and potential. Tensors of rank 2. A set of 9 physical quantities that transform under rotations, and for example, we can take quantities like moment of inertia, the stress tensor, and the strain tensor, Vectors are tensors of rank 1. So for scalars, phi prime is equal to phi, whereas for tensors of rank 2, the transformation equation can be written as capital T prime subscript I subscript j is equal to a subscript I subscript k times a subscript j subscript l times capital T subscript k subscript l. Pseudo tensors. Now let us do the generalization of the definitions that we have discussed above of the tensors to higher ranks. So let us now define tensor of rank 3. So if we take a tensor of rank 3, then and if we do a transformation from the unprimed coordinate system to the primed coordinate system, then the transformation coefficients will be a total of 27 quantities, and this can be defined as, let's say m is the quantity which is transforming from the unprimed to the primed coordinate system, then m prime subscript I subscript j subscript k is equal to a subscript I subscript l times a subscript j subscript m times a subscript k subscript n times m subscript l subscript m subscript n, where the quantities a subscript I subscript l, a subscript j subscript m, and a subscript k subscript n are the coefficients which execute this transformation. In a similar manner, we can extend this kind of a transformation to even higher rank tensors. And since this kind of a transformation is normally not required, therefore we can avoid its discussion over here. Now let us now come to another important quantity which is called the pseudo tensors. So if we have the direction cosines such that they satisfy the equation A transpose times A is equal to the identity matrix I, then from this we have the determinant of A is equal to either +1 or -1. Now for pure rotation, the determinant of A turns out to be 1, while if the operation is of inversion or reflection, then the determinant of A turns out to be -1. And if the operation involves both inversion with rotation, then the determinant of A is again -1. And this can be seen from the above argument that for an inversion or reflection operation, the determinant of A is -1, and then if it is followed by a rotation or vice versa, then since for pure rotation the determinant of A is 1, so -1 times 1 will give a -1. Therefore, for these two operations taken together, that is for inversion with rotation, the determinant of A turns out to be -1. Now let us look at the physical objects and how they may have different properties under inversion. So first of all, let us consider a scalar quantity. Then if a scalar quantity defined by phi undergoes an inversion operation from phi to phi prime, then we see that this is invariant under such an operation and phi prime turns out to be equal to phi. However, if we consider a scalar quantity which undergoing this inversion operation changes its sign, that is, as phi goes from phi to phi prime, then phi prime is equal to minus of phi, then such a scalar quantity is called as a pseudo scalar quantity. Similarly, a pure vector will change sign under inversion. That is, if a vector A goes to vector A prime under the operation of inversion, then vector A prime is equal to minus of vector A. Playing with indices. Now let us define pseudo or axial vectors. A vector that does not change sign under inversion is called a pseudo or axial vector. So if we look at the transformation, vector B going to vector B prime, such that vector b prime is equal to vector b, where vector b prime is the vector obtained under the operation of inversion. And the example of such pseudo or axial vectors are cross product of two pure vectors, such as angular momentum. A pure tensor of even rank does not change sign under inversion, and that of odd rank does. Similarly, if we look at the converse, if a tensor of even rank is changing sign under inversion, or a tensor of odd rank does not change sign under inversion, then such tensors are called pseudo tensors. Playing with indices. Now let us look at two vectors, vector A and vector B, and we make a tensor of rank 2 given by T subscript I subscript j is equal to A subscript I times B subscript j. Then the tensor T prime subscript I subscript j is equal to A prime subscript I times B prime subscript j, and this can be given as under the transformations that we have defined: small a subscript I subscript k times capital A subscript k times small a subscript j subscript L times capital B subscript L, and this can be written as small a subscript I subscript k times small a subscript j subscript L times capital A subscript k times capital B subscript L, and this can then be written as small a subscript I subscript k times small a subscript j subscript L times capital T subscript k subscript L. So if we now contract the two indices, we get a scalar. For example, T subscript I or T prime subscript I is equal to A subscript I subscript k times A subscript I subscript L times T subscript k subscript L, and this is equal to Kronecker delta subscript k subscript L times T subscript k subscript L, and this is equal to T subscript k subscript k. Given a tensor of any order, contracting any two indices gives a tensor of rank lower by 2. Tensors of higher rank can be obtained from those of lower rank by multiplication. Two special tensors. Now let us define two special types of tensors which we will be using extensively in our discussion of electrodynamics. The first of these two special types of tensors is the Kronecker delta operator. So the Kronecker delta is defined as delta subscript I subscript j, and this is equal to 1 if I is equal to j, and this is equal to 0 if I is not equal to j. Another important tensor that we need to define over here is the permutation tensor, which is denoted by epsilon subscript I subscript j subscript k. This is equal to 1 if I, j, k indices take the value 1, 2 or 3 or a cyclical combination of these three numbers. That is, I, j, k can take the values 1, 2 and 3 respectively, or can take the values 3, 1 and 2 respectively, or can take the values 2, 3, 1 respectively. Similarly, this permutation tensor epsilon subscript I subscript j subscript k turns out to be -1 if the indices I, j and k take the values 1, 3 and 2 respectively, or take the anticyclic combination. That is, the indices I, j and k take the value 1, 3 and 2 respectively, or the value 2, 1 and 3 respectively, or the value 3, 2, 1 respectively. And the permutation tensor epsilon subscript I subscript j subscript k turns out to be equal to 0 if any two or all of the three indices I, j, k are equal. So from the above discussion, one can conclude that the permutation tensor epsilon subscript I subscript j subscript k is equal to epsilon tensor subscript j subscript k subscript I is equal to epsilon tensor subscript k subscript I subscript j. Also, if we take the product of these two permutation tensors, that is epsilon tensor subscript I subscript j subscript k times epsilon tensor subscript I subscript L subscript m, then this turns out to be equal to Kronecker delta subscript j subscript L times Kronecker delta subscript k subscript m minus Kronecker delta subscript j subscript m times Kronecker delta subscript k subscript L. The cross product of two vectors a and b that we had defined earlier in terms of the permutation tensor can be rewritten as cross product of vector a and vector b subscript I is equal to epsilon subscript I subscript j subscript k times a subscript j times b subscript k. Now let us look at the proof of the vector identities via tensor notation. So if we consider the vector triple product of three vectors, that is vector a, vector b and vector c, then vector a cross within brackets vector b cross vector c is equal to vector b times within brackets vector c dot vector a minus vector c times within brackets vector a dot vector b. In the tensorial notation, this vector triple product can be written as vector a cross within brackets vector b cross vector c bracket close whole brackets subscript I is equal to epsilon subscript I subscript j subscript k times a subscript j epsilon subscript k subscript L subscript m times b subscript L times c subscript m. This result we have obtained using the definition of the cross product that we have defined above, and then this can further be written as epsilon subscript I subscript j subscript k times epsilon subscript k subscript L subscript m times a subscript j times b subscript L times c subscript m, and this is equal to epsilon subscript k subscript I subscript j times epsilon subscript k subscript L subscript m times a subscript j times b subscript L times c subscript m. Here what we've done is that in the first epsilon tensor or the permutation tensor, we have taken a cyclical combination of ijk where we have brought k as the first index. And this we have done because then we can utilize the other property of the permutation tensor that we had defined above with respect to the Kronecker delta, and using that property we get the result bracket open delta subscript I subscript L times delta subscript j subscript m minus delta subscript I subscript m times delta subscript j subscript L whole bracket close times a subscript j b subscript L c subscript m, and this is equal to a subscript j b subscript I c subscript j minus a subscript j times b subscript j times c subscript I, and this is nothing but the result that we had obtained above, which is equal to bracket open within brackets vector a dot vector c times vector b minus within brackets vector a dot vector b bracket close times vector c whole bracket close subscript I. Curvilinear coordinates. Now, a number of times, depending upon the symmetry of the problem, it is possible that the Cartesian coordinate system may not always be suitable. And in such cases, there might be other coordinate systems which might be more suitable. And like I mentioned earlier, that this suitability generally depends upon the symmetry of the problem. So for systems which have a cylindrical symmetry, it is more convenient to use cylindrical coordinate system, while systems which have a spherical symmetry, it is better and more convenient if the spherical polar coordinate system is used. So now let us define the spherical polar coordinate system. So let us again consider the Cartesian coordinate system with origin at O and the three axes, that is the x, the y and the z axes. And then now let us define the spherical polar coordinates with respect to this Cartesian coordinate system. So for a point P in the Cartesian coordinate system, the distance from the origin is given by the position vector r, and the magnitude of the distance is r vector magnitude or modulus. The angle which the projection of the point P from O, that is OP, makes on the xy plane with the x-axis is phi, and this is called the azimuthal angle, while the angle which the line OP makes with the z-axis is the polar angle and is denoted by theta. So in case of the spherical polar coordinate system, the three coordinates are, instead of x, y and z, they are theta and phi, where r is the distance from the origin of the point P, theta is the polar angle that the line OP makes with the z-axis, and phi is the azimuthal angle which the projection of the line OP on the xy plane makes with the x-axis. And the range of these three coordinates are, r will vary from 0 to infinity, theta will take values from 0 to pi, and phi can take values from 0 to 2 pi. And if we want to write down the relation with the Cartesian coordinate system, then the Cartesian coordinate x is equal to r times sine of theta times cos of phi. Cartesian coordinate y is equal to r times sine of theta times sine of phi. And Cartesian coordinate z is equal to r times cos of theta. Spherical polar coordinates. Now the unit vectors of the spherical polar coordinate system are denoted by unit vector r, unit vector theta and unit vector phi. And these unit vectors in terms of the unit vectors of the Cartesian coordinate system, that is unit vector x, unit vector y and unit vector z, are given by the relations unit vector r is equal to sine of theta times cos of phi times unit vector x plus sine of theta times sine of phi times unit vector y plus cos of theta times unit vector z. Unit vector theta is equal to cos of theta times cos of phi times unit vector x plus cos of theta times sine of phi times unit vector y minus sine of theta times unit vector z. And unit vector phi is given by the relation minus sine of theta times sine of phi times unit vector x plus sine of theta times cos of phi times unit vector y. And just like unit vector x, unit vector y and unit vector z make an mutually orthogonal basis set in the Cartesian coordinate system, similarly unit vector r, unit vector theta and unit vector phi together form a mutually orthogonal basis set in the spherical polar coordinate system. The directions of unit vector r, unit vector theta and unit vector phi are not fixed in space, but these directions change with the point P. For example, the direction of the unit vector r will always be along the line joining the origin to the point P. So if the point P changes, then similarly this direction also changes. The direction of the unit vector theta is perpendicular along the line OP and will lie in a direction which is defined by, if we take the z-axis and then move from the z-axis onto the line OP, then the plane defined by such a movement, the unit vector theta will be normal to this movement, or rather I should say will be tangential to this movement, while the unit vector phi will again be perpendicular to the line OP, but the direction will be tangential to the movement of the x-axis towards the projection of the line OP on the xy plane. Now, let us see that while doing the differentiation of these three unit vectors, that is unit vector r, unit vector theta and unit vector phi, we then get the infinitesimal displacement in the polar coordinates as dl vector is equal to dr times unit vector r plus r times d theta times unit vector theta plus r times sine of theta times d phi times unit vector phi. Thus, in this manner, we have defined an infinitesimal displacement in the spherical polar coordinates, where dr, d theta and d phi are the infinitesimal displacements in the spherical polar coordinate system. And the infinitesimal volume element in the spherical polar coordinate system, that is dv, is equal to r square times sine of theta times dr times d theta times d phi. And the spherical polar components of a vector quantity A defined by vector A are a subscript r times unit vector r plus a subscript theta times unit vector theta plus a subscript phi times unit vector phi, where a subscript r is the component of the vector A along the unit vector r, a subscript theta is the component of the vector A along the unit vector theta, and a subscript phi is the component of the vector A along the unit vector phi. Vector derivatives in polar coordinates. Now let us define the different vector operations or the derivative operations that we had defined earlier in the Cartesian coordinate system in the current spherical polar coordinate system. So first of all, let us define the gradient of a vector quantity. So the gradient of a scalar v is defined as gradient v is equal to del v by del r times unit vector r plus 1 by r times del v by del theta unit vector theta plus 1 by r sine theta times del v by del phi unit vector phi. The next operation that we need to define is the divergence of a vector quantity A. So the divergence or the del dot vector A is equal to 1 by r square times del by del r within bracket r square times a subscript r bracket close plus 1 by r sine theta times del by del theta bracket open sine theta times a subscript theta bracket close plus 1 by r times sine theta whole times del by del phi acting on a subscript phi, where a subscript r is the r component of the vector a subscript theta is the theta component of the vector A, and a subscript phi is the phi component of the vector A. Then let us now define the curl of the vector quantity A. So the curl or the del cross A of the vector quantity A is equal to 1 by r times sine theta whole times bracket open del by del theta bracket open sine theta times a subscript phi bracket close minus del by del phi acting on a subscript theta whole bracket close whole times unit vector e subscript r plus bracket open 1 by r times sine theta whole times del by del phi acting on a subscript r minus 1 by r times del by del r bracket open r times a subscript phi bracket close whole bracket close times unit vector E subscript theta plus 1 by r times bracket open del by del r bracket open r times a subscript theta bracket close minus del by del theta a subscript r whole bracket close times unit vector E subscript phi, where unit vector E subscript r is the unit vector along the r direction, unit vector E subscript theta is the unit vector along the theta direction, and unit vector E subscript phi is the unit vector along the phi direction. And then we define the Laplacian of a scalar quantity V as del square V is equal to 1 upon r square times del by del r bracket open r square del V by del r bracket close plus 1 by r square sine theta times del by del theta bracket open sine theta del V by del theta bracket close plus 1 by r square sine square theta whole times del 2 by del phi square V bracket close, and this is equal to 1 by r del square by del r square acting on r times V plus 1 by r square sine theta del by del theta bracket open sine theta del V by del theta bracket close plus 1 by r square sine square theta times del square by del phi 2 acting on V. Cylindrical coordinates. Now let us look at another type of coordinate system which is normally used and which is called the cylindrical coordinate system. This kind of coordinate system is generally used for problems which have a cylindrical symmetry or for systems which have cylindrical symmetry. So here again we choose the same origin and the axis as in the Cartesian coordinate system, and the point P in the cylindrical coordinate system will have the coordinates defined by rho, phi and z, where rho is the distance from the origin of the projection of point P on the xy plane, phi is the azimuthal angle that the projection of OP on the xy plane makes with the x-axis, and z is the distance along the z-axis of the point P. And the range of the three coordinates in the cylindrical coordinate system, that is rho, phi and z, is given as rho can vary from 0 to infinity, phi can vary from 0 to 2 pi, and z can vary from minus infinity to plus infinity. And the coordinates in the Cartesian coordinate system in terms of the coordinates in the cylindrical coordinate system are given as x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. And the unit vectors of the cylindrical coordinate system are given by unit vector rho, unit vector phi and unit vector z, and the direction of these unit vectors in terms of the unit vectors of the Cartesian coordinate system, that is unit vector x, unit vector y and unit vector z, is given as unit vector rho is equal to cos phi times unit vector x plus sin phi times unit vector y. Unit vector phi is equal to minus sin phi times unit vector x plus cos phi times unit vector y. And unit vector z is equal to unit vector z. Vector derivatives in cylindrical coordinates. Now let us define the vector derivative operations in cylindrical coordinates. So first let us define a vector quantity in cylindrical basis. So the vector A in cylindrical basis is defined as A subscript rho times unit vector rho plus A subscript phi times unit vector phi plus A subscript z times unit vector z. And the infinitesimal displacement that might be there in a cylindrical coordinate system in terms of the infinitesimal elements of the cylindrical coordinate system is defined as vector dl is equal to d rho times unit vector rho plus rho d phi times unit vector phi plus dz times unit vector z. And the infinitesimal volume in the cylindrical coordinate system is defined as dv is equal to rho times d rho times d phi times dz, where d rho, d phi and dz are the infinitesimal elements of rho, phi and z in the cylindrical coordinate system respectively. Now let us define some of the derivative operations in the cylindrical coordinate system. So the gradient of a scalar v is defined as del v by del rho times unit vector rho plus 1 by rho times del v by del phi times unit vector phi plus del v by del z times unit vector z. Similarly, the divergence of a vector quantity A, where the vector A has been defined in the cylindrical basis above, can be written as divergence of vector A is equal to 1 by rho times del by del rho bracket open rho times A subscript rho bracket close plus 1 by rho times del A subscript phi by del phi plus del A subscript z by del z, where A subscript rho is the component of vector A along the rho coordinate, A subscript phi is the component of vector A along the phi coordinate, and A subscript z is the component of A along the z coordinate. Similarly, we can define the curl of the vector quantity A as curl of vector A is equal to bracket open 1 by rho times del A subscript z by del phi minus del A subscript phi by del z whole bracket close times unit vector rho plus bracket open del A subscript rho by del z minus del A subscript z by del rho bracket close whole times unit vector phi plus 1 by rho times bracket open del by del rho bracket open rho times A subscript phi bracket close minus del A subscript rho by del phi bracket close whole times unit vector z. And the Laplacian operator for a scalar quantity v is defined as Laplacian operator del square v is equal to 1 by rho times del by del rho times vector open rho times del v by del rho bracket close plus 1 by rho square times del square v by del phi square plus del square v by del z square. The Dirac-delta function. Now let us consider a vector function where vector A as a function of vector r is equal to 1 by r square times unit vector r. Using the divergence formula in spherical polar form, we can write the divergence of this vector function as defined above as divergence of vector A is equal to 1 by r square times del by del r bracket open r square A subscript r bracket close, and this turns out to be equal to 0. But if we look at the Gauss's divergence theorem, then the volume integral of the divergence of the vector A over the volume element d cube x is equal to the surface integral of the vector A dot unit vector n times the unit vector n is the unit normal of the surface element dA, and this turns out to be equal to 1 by r square times integral with limits going from 0 to pi over r square sine theta evaluated over d theta times integral over d phi with limits going from 0 to 2 pi, and this turns out to be equal to 4 pi. Now here there is, as we can see, some kind of an anomaly. While the divergence of the vector function A as we have defined above turns out to be 0, but if we use the Gauss's divergence theorem and evaluate the volume integral over this vector function A in terms of the divergence, then it turns out to be 4 pi. And the reason for this anomaly is that while the divergence of the vector function A is 0, it is so everywhere except at the point where r itself is 0. And there, this divergence goes to or diverges to infinity. And it's because of this that the integral over any volume of this divergence of the vector quantity A or the vector function A which contains that point at which this diverges to infinity will always be finite. That means the volume integral divergence of such a function will always be finite. And this is similar to the density of a point particle. And this leads to a definition of an operator or a function which we call as the Dirac-delta function. Dirac-delta function in one dimension. Now, from the discussion that we were just having regarding the vector function A as a function of vector r is equal to 1 upon r squared times unit vector r, and where we saw that the divergence of this vector function is 0, but the volume integral of the divergence according to the Gauss's divergence theorem gives a value of 4 pi. So using these properties of this vector function, we can actually define the Dirac-delta function as delta x is equal to 0 for all values of x not equal to 0 and is equal to infinity for x equal to 0. And the integral of this Dirac-delta function delta x over dx with limits from minus infinity to plus infinity is equal to 1. Here it is important to note that these limits as defined in the integral above need not necessarily be from minus infinity to plus infinity. What is important is that the limits of this integral must include the point where the argument is 0. And if we want to visualize, or if we want to get an idea of what this is, then we can think of a spike function with a high peak and a very narrow peak. That is, height is very high, but the width of that spike is very narrow, such that the width tends to 0 as the peak tends to infinity, and this encloses a unit area in the limit where the height goes to infinity and the width goes to 0. So in this manner, one can visualize this Dirac-delta function as a spike function, and by this definition that we have just defined, we can then regard this Dirac-delta function as a limit of a sequence of ordinary functions. So the Dirac-delta function delta x is equal to limit epsilon tending to 0 plus delta subscript epsilon as a function of x, where delta subscript epsilon as a function of x is equal to 1 upon twice epsilon for modulus of x less than epsilon, and is equal to 0 for modulus of x greater than epsilon. Dirac-delta function in one dimension. So some other forms of this delta subscript epsilon as a function of x is equal to 1 upon under root 2 pi times epsilon whole times e to the power minus of x square by twice epsilon square. Another form of this Dirac-delta function is delta subscript epsilon as a function of x is equal to 1 upon pi times epsilon upon x square plus epsilon square. Yet another form can be written as delta as a function of x is equal to 1 upon 2 pi times integral over dx of the function e to the power iota times k times x with limits going from minus infinity to plus infinity. And this can be written as limit alpha tending to infinity sine of alpha times x upon pi x. Now if we consider any ordinary function f as a function of x, then the function f as a function of x times the Dirac-delta function as a function of x minus a is equal to f as a function of a times Dirac-delta function x minus a. Rewriting this equation and taking the integral on both sides with respect to x, we get integral of the function f as a function of x times delta as a function of x minus a over dx with limits from minus infinity to plus infinity is equal to the integral f as a function of a times delta function as a function of x minus a over dx with limits minus infinity to plus infinity, and this turns out to be equal to f as a function of a. Properties of the delta function. Here it is important to note that while the delta function delta x itself may not be a very legitimate function, that means may not be a function which can be defined properly, but the integral involving this delta function is legitimate. That means its value can be defined properly, and therefore it is often seen this delta function is used or appears only under an integral sign. Another important property of the delta function is that if we have two expressions which involve this delta function and which upon integration give the same result, then the two expressions can be considered as equivalent. In this sense, we can define the following identities. Delta as a function of x is equal to delta as a function of minus x. Delta prime as a function of minus x is equal to minus of delta prime as a function of x. Using these definitions, we can then write x times delta prime as a function of x is equal to minus of delta as a function of x. Also, delta as a function of a times x is equal to 1 upon modulus of a times delta as a function of x. And delta as a function of x square minus a square is equal to 1 upon twice modulus of a whole times bracket open delta as a function of x minus a plus delta as a function of x plus a bracket close. And then we have delta as a function of g, which in itself is a function of x, is defined as summation over I 1 upon modulus of g prime as a function of xi whole times delta as a function of x minus xi, where the subscript I basically denotes the subscript according to the coordinate system. Here in the last identity that we have written, or rather the last inequality that we have written, the x subscript I are the zeros of the function g as a function of x, that is g as a function of xi is equal to 0. Dirac-delta function in 3 dimensions. Now let us do the generalization of the Dirac-delta function to 3 dimensions. So del cube as a function of vector r is equal to del as a function of x times delta as a function of y times delta as a function of z, where the vector r is given as x times unit vector x plus y times unit vector y plus z times unit vector z, and this vector r is the position vector of a point. Similarly, if we were to take the volume integral over the Dirac-delta function, defined as volume integral over all space with respect to the volume element d cube x of the Dirac-delta function delta cube as a function of vector r, and this is equal to the triple integral over dx times dy times dz acting on the Dirac-delta function delta as a function of x times delta as a function of y times delta as a function of z, and this turns out to be equal to 1. So this identity can be proved from the result that we had seen in the Dirac-delta function in 1 dimensions. So if we extend that result to 3 dimensions, then we can get the current result. And the volume integral over all space over the volume element d cube x of the function f as a function of vector r times the Dirac-delta function delta cube as a function of vector r minus vector a is equal to the function f as a function of vector a. Here vector a is such that when vector r is equal to vector a, then the Dirac-delta function tends to infinity, otherwise it will give the value 0. Now let us define the Dirac-delta function in the spherical polar coordinates. It can be written as delta cube r vector minus r prime vector is equal to delta as a function of r minus r prime times delta as a function of theta minus theta prime times delta as a function of phi minus phi prime whole divided by r square times sine theta. Here again we can understand the Dirac-delta function for r equal to r prime goes to infinity and for all other values of r is 0. Similarly, the Dirac-delta function for theta equal to theta prime goes to infinity and for all other values of theta is 0, while the Dirac-delta function for phi equal to phi prime goes to infinity and for all other values of phi is equal to 0. Similarly, the Dirac-delta function in cylindrical coordinates can be defined as delta cube vector r minus vector r prime is equal to delta as a function of rho minus rho prime times delta as a function of phi minus phi prime times delta as a function of z minus z prime whole divided by rho. Here again, the delta function goes to infinity for rho equal to rho prime and is 0 for all other values of rho. Similarly, the delta function goes to infinity for phi equal to phi prime and is 0 for all other values of phi, and the delta function goes to infinity for z equal to z prime and is 0 for all other values of z. Resolution of the paradox. Now let us look at the divergence of the function a as a function of vector r that we had defined above, which was that the function a as a function of vector r is equal to 1 upon r square times the unit vector r. Then we saw that the divergence of this function a turns out to be 0 everywhere except at the origin, that is, except where r tends to 0. However, when we evaluated the integral of this divergence of this function a, that is, we used the Gauss's divergence theorem for this function a, then we found out that the integral turns out to be finite. And it was this result that we used to define our Dirac-delta function. Now let us look at the divergence of this function a and define this divergence in terms of the Dirac-delta function. Then the divergence of the function 1 upon r squared times unit vector r turns out to be equal to 4 pi times delta cube as a function of vector r, where delta cube as a function of vector r is the Dirac-delta function and is defined such that it gives the value 0 for all values of vector r except where the modulus of vector r is equal to 0, where this Dirac-delta function diverges to infinity. So now if we define the separation between the two position vectors defined by the position vector r and the position vector r prime such that the vector capital R is equal to the position vector r minus the position vector r prime, then the divergence of the function 1 upon capital R square times unit vector r is equal to 4 pi times delta cube as a function of vector capital R. Now, since we know that the gradient of the function 1 by capital R is equal to minus of 1 by r square times unit vector r, therefore we use the Laplacian operator for this function 1 upon capital R, and the Laplacian operator acting over this function 1 upon capital R is equal to del operator dot del operator acting on the function 1 over capital R. This turns out to be equal to del operator dot within brackets minus of 1 by r square times unit vector capital R, where this result we have taken from the way we had defined the divergence of the function 1 upon capital R, and this then turns out to be equal to minus 4 pi times delta cube as a function of capital R vector, where this result we have taken from the way we have defined the divergence of the function 1 upon capital R squared times unit vector R. So students, now let us summarize what we have learned in this module. We have first learned the general and useful definition of vectors through their properties under rotations. The idea is then generalized to other physical objects called tensors that have more complicated properties under rotations of the coordinate system. The idea of general curvilinear coordinates is introduced and their usefulness discussed. Two of the most often used curvilinear coordinate systems, the spherical polar coordinate system and the cylindrical coordinate systems, are then discussed in detail. A new kind of function called the Dirac-delta function is introduced, first in one dimension and then in three dimensions. The usefulness, rather indispensability of the function in vector analysis is described through an example. Many of its useful properties are then described. Thank you.